Dear student, today we are discuss about topic buffer solution, which is a part of the chapter Ionic Equilibrium. So first of all, we want to know what are buffer solution. Those solution which resist change in pH on adding strong acid and strong base. So first of all, we write definition of buffer solution. Solution which resist change in pH that we take a buffer solution. This is buffer solution. If we add strong acid and strong base, if we added strong acid and strong base in a small amount and on dilution, pH remain constant. So it is necessary, we want to know what are buffer solutions. Okay, student, in today's world, in medicine industry and pharma industry, it is necessary to maintain buffer. And in our blood pH, buffer is maintained by bicarbonates ion. So it is importance of the buffer solutions, because in medicine industry to maintain buffer, it is very essential, because some enzymatic action are done on a particular pH. If pH change, then the efficiency of the enzyme is also changed. Then we know the graph of the enzyme efficiency, enzyme activity and pH. So enzyme, biocatalyst enzyme are effective on a particular amount of pH, which is a bell-shaped curve. If pH is changed by a small amount, then the enzyme efficiency change in our body. So it is essential for buffer solutions. Okay, students, next slide we discuss about types of buffer solution and how we prepare buffer solution. Okay, students. Dear student, now we discuss about buffer action. The ability of a buffer solution to consume extra added H plus ion and OH minus ion. So now we discuss ability to consume extra added H plus and OH minus ion. Dear student, if we take a buffer solution, like this is a buffer solution of NH4Cn. So the parent ion of the NH4Cn, it come from weak base NH4OH, and the Cn is came from weak acid SCN. So we know that it is a part of the weak base NH4 ion, and Cn minus ion is the part of weak acid. So they both take place in hydrolysis. Okay, so NH4 ion, NH4 positive ion remain in solution, and Cn minus ion in buffer solution. If we added extra amount of H plus in buffer solution and OH minus ion, so we now see the action of buffer solution. If we add extra amount of OH minus ion, which is consumed by NH4 positive ion and form NH4OH. Okay, student, and we added extra amount of acid, strong acid, which is consumed by cyanide ion. So the effect of the extra added H plus and OH minus ion is neglected. So this action done by buffer solution is known as buffer action. Okay, student, now we discuss about types of buffer solution. Okay, now we discuss about types of buffer solution. Buffer solution can be classified into two types. First is mixed buffer, and the second is simple buffer. Okay, student. simple buffer contain only one component, so it is called simple buffer. It contains only one component. Basically, it is the salt of the weak acid and weak base formed by salt of weak acid and weak base. That for we take example NH4Cn. It is the NH4 positive ion, it is the part of the weak base, and Cn minus ion, it is the part of weak acid. So after neutralization reaction of weak base and weak acid, the formation of their salt take place. Okay students, so it is act as a simple buffer solution. And now we discuss about mixed buffer. Mixed buffer contain two components, so it is called mixed buffer. Further, mixed buffer can be classified into two types. First is acidic buffer, second is basic buffer. Okay student. First of all, we discuss about acidic buffer. Acidic buffer formed by the weak acid plus its salt. Its salt. We can say that weak acid and its conjugate, or we can say that weak acid plus its salt with, we can write salt with strong base. That we take one example, a weak acid CH3COH plus its salt with strong base CH3COONA. And next type of mixed buffer is basic buffer. So basically, basic buffer is formed by weak base and its salt with strong acid. Okay student, so we further write that, for example, weak base plus its salt with strong acid. That we can take example NH4OH plus its salt with a strong acid NH4Cl. So basically it contains two components. The mixed buffer solution contains two components. So it is called mixed buffer. That in its basic buffer is also contain two components, dear student. So it is called mixed buffer. Okay student. And in simple buffer only the one component act as buffer solutions. So it is called simple buffer. Next slide we can discuss further about buffer solution of simple buffer action. Okay student. Now we discuss about simple buffer. How can we simple buffer act? So the simple buffer is the case of the third case of hydrolysis. Okay student. It is nothing but it is the case of the third case of hydrolysis. Third case of salt hydrolysis. We know about the third case of hydrolysis. In this hydrolysis, the hydrolysis takes place of the salt of weak acid and weak base. Okay student. In this hydrolysis take place of salt of weak acid and weak base. Example NH4Cn. So its pH calculate easily by the third case of hydrolysis pH formula, in which concentration not effect. Okay student. So we know that the hydrolysis constant of the third case of hydrolysis, okay student, it is further calculated by root kh, okay student. So root kh is further right at, we know, by the third case of hydrolysis KAB. So its pH formula can be derived as pKa minus pKb. So we say in this formula there is no effect of concentration, no term of concentration is come here. In the first and second case of the salt hydrolysis, log C of the concentration term come, but here it not come. So simple buffer not affected. Why adding H plus or OH or further change in concentration. We know that molarity is number of moles per unit volume. If we change the volume, if we dilute, on dilution increase in volume take place, so change in concentration take place. Okay student, concentration become decreases, so change in volume, concentration decrease. But in the formula of the third case of hydrolysis, there is no term of the concentration term appears here. So if we change the concentration, there is no effect on the pH of the salt of weak acid and weak base. So simply buffer action take place. Okay student. Now we discuss about mixed buffer. Mixed buffer are classified into two types, acidic and basic buffer. Now we detail discuss how we prepare acidic buffer and basic buffer. The first method of the preparation of the acidic buffer is, first is we take weak acid plus its salt with strong base. And the first method of the preparation of the basic buffer, we take here we take weak base. In acidic solution we take acidic buffer, we take weak acid, and basic buffer we can weak base, that's its salt with strong acid. Okay student, now we can take an example. Here weak acid CH3COH, let is salt with strong bases CH3CONA. Okay student, here basic buffer, weak base is a NH4OH, let is salt with strong acid NH4Cl. Now the second method of the preparation of acidic buffer is, we take weak acid with strong base. If here after the further reaction, if strong base is present as a limiting reagent, then only buffer solution take place, formation of buffer solution take place. Okay student, so here the moles of weak acid is greater than the moles of strong base, then only the formation of the buffer solution take place. If we can take an example of a weak acid, and further after reaction, if we take 10 moles of weak acid and we take strong base in limiting reagent as a limiting reagent, okay student, then further after reaction, acid base reaction take place in solution. Okay, here formation of CH3CONA plus H2O. After neutralization reaction, there is the formation of the salt and water take place, you know student. Okay, then here the 5 moles of the NaOH, because NaOH present in a limiting amount. Okay student, here the 5 moles of weak acid in solution, and the here full consumption of the strong base take place. Okay student, and the formation of 5 moles of salt of weak acid salt of weak acid student. So here in after the reaction in solution, only 2 component. Okay student, here remains only weak acid, and the salt of weak acid with strong base remains in solution. So it is further can be said the formation of the buffer solution take place. It is satisfies the first condition. Then we can further discuss about the second type of the formation of the basic buffer. Okay, basic buffer formed by the weak base plus strong acid. Here is also the condition after the reaction. Neutralization reaction takes place here. If acid and base is present, then neutralization reaction is take place here. Here also a condition. Here the moles of the weak base is greater than the moles of strong acid. Then only the formation of buffer take place student. Okay, now we can see the example. We take a strong acid like HCl. Okay, here we fulfill this condition. Okay, the moles of the weak base is in excess amount and the strong acid in limiting reagent amount. Okay student, so after further neutralization reaction take place, okay, then the formation of after the neutralization reaction salt and water. Okay student, so after we see this is present in excess amount. So while limiting reagent is consumed completely in reaction, 5 moles of limiting reagent consumed completely. Okay, because reaction is take place as while limiting reagent. Okay student, so after reaction 5 moles of weak acid, and here the formation of 5 moles of its salt, weak acid salt with strong base take place. Okay student, so after reaction solution, in solution only 2 components remain, so these can act as basic buffer. So here is also we can fulfill the first condition, weak base plus salt with strong acid, it is remain in solution. So now after the reaction it solution act as a basic buffer. Okay student, now we discuss further third case of the formation of the acidic buffer and basic buffer. If in exams a question is come, if in acidic buffer, if salt of weak acid with its conjugate is given. Okay student, and with its a strong acid is also given. Okay student, and basic buffer is salt of its conjugate, weak base and salt with its conjugate is given. Okay student, and strong base is given. Then there after further reaction we want to check that it can act as buffer or not. If moles of here, moles of is in excess amount, then strong acid, and here the moles of this salt of weak acid with its strong base is greater than strong base, then buffer solution take place. Formation of student, now we can derive Henderson equation for acidic buffer and basic buffer. We know that the formation of acidic buffer it takes place by weak acid and its salt with strong base, and the formation of basic buffer formed by weak base and salt with strong acid. We can already teach that. Okay student, so further we write the dissociation constant for weak acid. Okay student, then K is written as, if initial amount the acid weak acid is present is A, then X moles is dissociated, so there the formation of CH3CO minus is X moles. Okay student, and this salt is S concentration is present, then it dissociates in ionic form. There is a concentration of CH3CO minus ion is S. Okay student, and it acts as a spectator ion in, because it is a part of weak base, strong base. Okay student, spectator ion does not take part in buffer action. Okay student, so we write Ka for this reaction. So first of all we write the concentration of CH3CO minus ion. Here we see here common ion effect is observed, common ion. So the concentration of both we can written here as CH3CO minus concentration S plus X, then H plus concentration, and here the reactant concentration A minus X. From common ion effect it is observed student that the formation of this CH3CO minus ion from weak acid is very less. X is very less than S. Okay students, so we neglect here the X. Okay, so we write Ka dissociation constant for weak acid S into H plus concentration upon acid concentration. Okay student, so it is the dissociation constant we write on taking log both sides, on taking minus log both sides. Okay student, if we take minus log on both sides, minus log K minus log salt by acid concentration minus log H plus. Okay student, we know already the minus log K is written as pK is equal to minus log salt by acid concentration minus log H plus is written as minus pH. Add pH. ठीक है student. Okay student, then the pH formula is driven as pH is equal to pK. On taking log S by A this side, we get the formula log salt by acid concentration. So it is Henderson equation for acidic buffer. So we derive the Henderson equation for acidic buffer solution. Here in formula you can written concentration salt concentration by acid concentration. Okay, direct you can write here moles, equivalence, okay student, then the formula fulfill all the condition and you become get answer. Now we can derive the Henderson equation for basic buffer. Dear student, you know here is the weak base, so dissociation constant for weak base is written as Kv. So we write first of all base, weak base is, let's suppose the concentration of weak base is V. Here the dissociation moles is X here, then the dissociation moles of X get V here. Okay student, and the salt is present as S, and the salt dissociation became S and S. Okay student, now we write dissociation constant for this weak base. The concentration for NH4 positive. Here also common ion effect is observed. Student, you can see here common ion effect is observed. So we write the NH4 positive concentration as plus X from both, and then OH concentration for this Kb, OH minus ion concentration, product by reactant, you know that from equilibrium. Okay student, then you know from here common ion effect, the formation of NH4 ion from weak base is very less. Here, so we can neglect the NH4 positive ion from weak base. Okay student, so we write Kb here, salt by base concentration into OH minus ion concentration. Okay student, which is come from weak base. On taking log both side, on taking minus log both side, for easiness to derive our formula, minus log both side. Okay, minus log Kb minus log salt by base concentration minus log OH concentration. Okay student, so you know that minus log Kb is written as pKb is equal to minus log salt by base concentration, and minus log OH is written as POH. Okay student, so we can now reciprocate POH is equal to pKb plus log salt by base concentration. Okay student, so it is the formula for Henderson equation for basic buffer. Okay student, now you use this directly formula in numerical problems. Here you can write similarly the concentration directly, salt concentration by base concentration, and moles, millimoles. Okay student, so we get the Henderson equation basic buffer. Next we discuss about the numericals which is come in our exams. Okay, now we discuss some question of our NEET exam. Okay student, so first question is which pair is not act as acidic buffer. For acidic buffer condition we study the weak acid plus its conjugate remain in solution, then it act as buffer solution. So first option is seen is CH3CON, it is a weak acid, and CH3CON it is conjugate. Okay student, so in question it is asked which pair is not act, so it is act as acidic buffer. And second option HClO4, you know that HClO4 is a strong acid. Okay student, so it is not the fulfill the condition of acidic buffer. So option, our right option is second. Okay student, and we can also see C option H3CO. H3CO is a weak acid and Na2CO3 is conjugate. Okay student, H3PO4 is also a weak acid and Na3PO4 is conjugate. So our right option is B, because this question is asked not act as a acidic buffer. Next we discuss second question. Okay student, the Ka for a weak acid is 10 to the power 4. The dissociation constant is given here for weak acid, and in order to prepare a pH, in question it is asked he prepare pH of 5. Okay student, so first of all we write Henderson equation of acidic buffer. Okay student, so pH equal to pK, it is Henderson equation for acidic buffer, log salt by acid concentration. So according to question, here it is a pH is given 5. They want to prepare a solution of 5 and pKa. For pKa we know that to find pKa formula minus log K concentration, which is given in question. So here minus log K concentration is given in question 10 to the power 4 minus 4. Okay student, so here pK is equal to 4. pK is equal to 4. So pK we can put here, pK is equal to 4 plus log salt y acid concentration. Then 5 minus 4 is equal to log salt y acid. Okay student, so here 1 is equal to log salt y acid. On taking anti-log, we get salt y acid concentration is equal to 10 y1. Okay student, so our right option is B. Now we discuss third question. The pH of blood from 7.26 to 7.23 is maintained by buffer. It is asked in AIMS. In our blood, buffer is maintained by bicarbonates ions and is conjugate. Okay student, because in cellular respiration CO2 is releases. So why our body become acidic. Okay student, it is maintained by buffer. So here it is a learning question. Okay student, so here bicarbonate ion you can see here the option is first. It is maintain pH of our blood. Now we discuss fourth question. Okay student, in a buffer solution, equal concentration of V minus and HV. HV means here weak base is given. Okay student, weak base, and the dissociation constant of weak base is 10 to the power minus 10. Then the pH is asked in question. Okay student, so we write Henderson equation for basic buffer. So Henderson equation for basic buffer, POH is equal to PKB plus log salt by base concentration. So student, you know here is given in question the salt and base concentration is equal here, equal. So the Kb is given. So first of all we calculate as same calculate here in this question, we calculate pKb for basic buffer solution. So pKb is equal to minus log Kb, simply Kb concentration. Okay student, so minus log here Kb is given 10 to the power minus 10. So pKb is equal to 10. Okay students, so we put in this formula pKb, POH is equal to pKb is 10 and plus if log salt y base concentration are equal, salt concentration is become taken 1 and base concentration is taken 1 because they are equal as in discussing question. Okay student, so log 1 here came, or we know that the value of the log 1 is 0. So POH is 10. We get POH is equal to 10. But in question pH is asked. You see that in question pH is asked. So from the chapter basics of ionic equilibrium, you know that the sum of pH plus POH is equal to 14. We study it is basics in ionic equilibrium. Okay student, so pH is equal to 14 minus POH. From this formula we get pH is equal to 14 minus POH. So pH is equal to, if we minus 14 minus POH, POH here is 10, so we get pH is equal to 4. So the right answer is 4. Okay. Now we discuss buffer range. Buffer range simply defined as the range over which the effectiveness of buffer solution is calculated. Okay student, so buffer range for acidic buffer lies between the salt by acid concentration if lies between 1 by 10 to 10. Okay student, if we put this solved by acid concentration and Henderson equation for acidic buffer solutions. The formula of Henderson equation for acidic buffer pH is equal to pKa plus log salt by acid concentration. If we put salt by acid concentration 1 by 10 one time and then put 10, it is pH lies between pH range lies between pKa plus minus 1. So it is the range for acidic buffer pH. Okay student, now we calculate buffer range for basic buffer. Buffer range for basic buffer. It also salt by base concentration it lies between salt by base concentration is lies between 1 by 10 to 10. If we put basic buffer Henderson equation this concentration, then we get POH is equal to pKv plus log salt by base concentration. If we put 1 by 10 here salt by base concentration, then 10, we get POH of basic buffer is lies between pKb plus minus 1. Okay student, if you want to calculate further pH, then basically we know that pH plus POH is equal to 14. From basic of this chapter you know that. Okay student, now we discuss next concept, waste buffer. For waste buffer action, waste buffer, if we want to prepare waste buffer, then for waste buffer the salt by acid or salt by base concentration is equal. Then we prepare waste buffer as from equation we write for pH is equal to pKb plus log salt by acid. For preparation of waste buffer solution, the salt by acid concentration is equal. If salt by acid concentration is equal, then pH is equal to pKa. Okay student, log salt by acid concentration is equal, then log 1 is written as, or we know that the value of log 1 is 0. So pH is equal to pKa student. Okay student, so we see one numerical on this waste buffer action concept. Okay student, question: a physician wishes to prepare a buffer at a pH 3.58. Okay, that effectively resists change in pH, yet it contains only small concentration of buffering agent. Which weak acid together its sodium salt best to use? So here ask which weak acid if we take for sodium salt to prepare waste buffer. Here our concept waste buffer. It is the concept of waste buffer. So we know that for waste buffer pH is equal to pKa. From this concept, from this key concept, pH is equal to pKa. Already we studied that for waste buffer mechanism pH is equal to pKa. So you cannot calculate anything in this question. You only see for waste buffer pH is equal to pKa, in which option is lies. Here pH is equal to pKa, in which 3.58. So option number second, acetic acid of pKa is equal to 3.58 act as waste buffer action as mechanism we can discuss already here. Now we discuss second question students. The Ka for weak acid is here 10 to the power minus 5 given buffer. Here a preparation of buffer take place can be used to maintain the pH in the range. Here first of all Ka is equal to given in this question 10 to the power minus 5. So pKa is equal to minus log Ka. Simply calculation we calculate pKa is equal to minus log K is given in question 10 to the power minus 5. Okay, so pK is equal to 5. Here in this question, the best range of the buffer is asked. So we already studied the buffer range of acidic buffer is lies pH. The pH for best buffer action lies between pK plus minus 1. So it is lies if in pK plus and minus 1, 5 plus 1 and 5 minus 1. So the answer is 4 to 6. So here option D is correct. Okay student. Now the topic is buffer capacity. Buffer capacity is denoted by 5. So we define buffer capacity. Buffer capacity is the number of the OH and H plus ions is added in 1 liter of buffer solution, then change in pH is take place per unit. It is called buffer capacity. So we write the formula of buffer capacity. It is denoted by 5. 5 is number of moles of H plus OH minus ions added in 1 liter buffer, then the change in unit, change in pH is called buffer capacity, student. So we write formula of buffer capacity: number of moles per unit volume added, then change in pH. Here delta pH is change in pH. So change in pH is become less when the buffer capacity is maximum, because it is inversely proportional. Okay student, so we discuss a question on buffer capacity. If a buffer solution, here 1 liter buffer we take, in this we added 0.04 moles of NaOH. If initial pH of buffer solution before adding is 5.80, after adding of 0.04 mole of NaOH, the pH final become 5.85. Okay student, so there is change in pH, some change in pH after adding 0.05 moles of NaOH in 1 liter buffer. So we can calculate 5 buffer capacity, number of moles of H plus and OH minus added in 1 liter of buffer. So the number of NaOH strong base added 0.04, then their delta pH, here change in pH final minus initial is, okay student, 0.05. Okay student, so we calculate buffer capacity, number of moles of strong base added 0.04 in 1 liter buffer, change in pH by 0.05. So this we can get 4/5.